this. Login one dot
So in this room we don't have microphones, but it doesn't matter. Now the microphone is in the computer.
Okay, so
More people in Vienna.
so yeah, then I'll try to be not too far away. So just let me know when you think we should start. So when.
You need to go out again the password. This one? Yeah, because I just changed the password. No, but they are asking. You need to write again the current password. Are you already changed it? Yes. So this is asking for the current password. But I know that this is try to do it. And I guess it's that.
So here would say can't. You don't want to store it on this computer. So it's just say can't. Because because it doesn't really have. And now you have to enter your password from it, and then you have to enter a password of your choice.
So the first time they ask to take the password, but first it asks again for the previous password. And then for the next one. So when you choose the password, you choose one classes or characters. So capital letters, small letters, number, exclamation. So who is not connected yet? Did you choose? Did you check it?
Yeah, I did, but
I think you need to generate the one.
yeah. No, yes, but it's not the yes, yes,
You will be asked to introduce it.
Once the connection is closed, you have to reconnect again using you can use on the keyboard. You can use SSH.
I mean, let me just show you.
if you already want to copy the PDF, then I mean, does it show in your sidebar? Oh. Okay. Just like, but I mean, this should show up here actually. But now I just hidden it. But the file should show up on this side. Let me just try to find them now. So, you know, if you click on this thing, then so you click on this little sphere, and then you have Theodore tutorial 3. You can just kind of click it and open it. Does yours have it? Yellow thing? You don't yellow thing. Oh yeah, you do. So like yellow spherical thing.
Yeah, I tried to replace it, but it's not working. I'm not getting on the folder, and I put maybe if I close them.
Yeah, it's. We were looking at this before. Some of them don't see the files in like this. It doesn't work for some of them. You don't see those files. No?
Okay, so how many of you were not able to log in? So how many are not logging? 1, 2, 3. Okay, so in order to move, I think maybe for today, or at least for this exercise, maybe you can sit together with a colleague, and then you share the computer, because otherwise we are going to be 2 hours trying to log in. Okay, so sorry. But we will try to solve it for the next. Yes, some of them, if you are with your password and
Yes. Okay.
and then you make a folder with your name. So we open a session with so who else is not able? So maybe some of you can open a session for them with your login details, and then you create a new folder. Okay? Okay, so those who were not able to log in, please ask to your person, the person who is next to you, to log in with the login details, please, with the password. Okay, the problem is if you try several times to change the password and you fail, then the account is blocked probably.
No, but
You can change the number of the and then you can have 3 of them. 1, 2, 3. Yeah.
no, you can cancel this part. The important part is
So do I want to? You are ready?
Yeah, so do. I'm just.
Yeah, I send by
No, maybe not.
Okay, so shall we kind of get started? So the idea is we're doing the first job in the theater tutorial. I mean, at this point, kind of the chemistry behind it is not so important. But let's say here we have two formaldehyde molecules, and and the idea is we could have a local excitation, a local excitation on one of them, or we could have charge transfer between them. And we're just trying to differentiate those two cases with Theodore. And it just turns out that because the system is symmetric, if we have a local excitation here, we'll also have a local excitation on this one. And if we have charge transfer this way, we also have to have charge transfer the other way. And then the question is, if you just kind of look at the canonical orbitals, then everything's going to be delocalized because both molecules are involved in the same way. And then the question is, the difference between these coupled local excitations and the charge resonance states is really just in the signs, how you combine the orbitals. So that's kind of the physics behind here. Then, so most of you are logged in. So then the next thing we can do is we have to load Theodore. So you say module load Theodore JMOL. I hope you can read this. Then we activate Theodore and JMOL as graphical output. So this is also written in this Word document here. Okay, so we run module load Theodore JMOL just to activate Theodore and JMOL. So by the way, please interrupt me if anything doesn't work for you. Otherwise, so feel free to stop me anytime. I'll just try to go through it. Okay. But so I'll do a few steps to get you started, and then we can also see that everyone catches up in case some people have not caught up. So then in this place you have a Theodore folder, and in some cases it works. That here on the left side you find this Theodore folder, and then you can just work with it like in the Windows Explorer. But if you don't have the Theodore folder, then you have to copy stuff back. Then you have to copy things back, and then you have to use the command that's shown here. Then you have to do scp -r your username at the server :Theodore space dot. So then you have to copy everything from this folder back to your local machine if you don't see it in the Explorer and Mobile Xterm. Okay, so then you have to run this command down here. So it's the same as you had for your login. Yeah.
I see Theodore, but it's not.
Yeah, and you just want to try logging out without logging in again.
No, mine's the same.
Maybe just press the exit, and then log in. Let's try one more time. Yeah. So if you don't see that, then then you have to use this scp command. So you scp -r, then the same login that you're using before, and then you just say copy the Theodore folder, and you copy whatever you want to copy it. So you can copy it to dot, onto desktop or somewhere wherever you'd want it to have it. Okay.
You have to do this from your node. You have to do this here from your node machine. So when you call this SCP command, you have to call this from your local machine. You have to open a new terminal and run it from your local machine. Felix, I need to copy from the local machine.
I mean, I just need them to have a document. I mean, a document with instructions.
Okay.
And then you open it.
But without logging, no logging. So from this computer,
Yeah, or I mean, maybe it's quicker if you just open this. I mean, you can. Yeah, I mean, you can also open it with an X server, but then it's a bit blurred. So I mean, you can. Or let's say. So you have to.
I don't know how you say
I mean, you can either call it, you can either copy it back, or you just open it on the remote server. So you can do something like events tutorial PDF and then open it on the remote server. That's the idea too. So, so either you copy it back, so then you have to open a new terminal that's on your local machine, and then use SCP to copy the content of this folder back. Or you open it on the remote machine. Yeah. Okay, yeah, and then. So now here, and I have to.
Yes.
I know
So where's mobile X? You know, then here I guess we go. Yeah, sure. You exactly. So that's, I mean, that's not I mean, you know, in a sense, mobile access is the combination of FileZilla and Apache, but it doesn't work. So,
no, there's no evidence, there's no anything here. Yes, yes, yes. But it's not a problem. I can I don't know. But you don't Yes. Okay, so now you go to yes, you but
So some of you have the file already open. So I think for the people that have the things open, I'll just kind of show you how we're going to proceed now. So let's say, you know, we might either open it by opening the PDF file remotely, for example, with events. So you here say events tutorial 3.pdf, and then you know, if you can't, let's see, hope it opens the PDF file now. Yeah, for example, here I have my PDF file, and this kind of walks me through what I'm doing. So, and you know, so the first thing is we just kind of type the command Theodore to see what there is. So let's say we can do Theodore, and this initiates Theodore. So basically when we do that, here my thing is a bit too small. But you know, when you initiate Theodore, then you see the header, and then you see a list of the different tools there are. So you know, even if you can't open the PDF, just type Theodore. So can you read this here? So you type Theodore. This is how you activate Theodore. And when you activate it, you see a list of all the different tools that there are. And then if you have some more, you know, if you want something about one of these tools, then you can say, for example, Theodore VMD plots -h, and then you get some information about this specific tool, what it does, and what options there are. Okay. So this is the basic mode of running Theodore to get all the different tools. So if you're logged in, you can do this now. You don't have to worry about downloading the PDF if the PDF doesn't work. Okay. So for the example that we're doing, we want this kind of this model system with two formaldehyde molecules next to each other. So so the first thing is we have to copy the input files. So you know, to get the input files. So you know, with Theodore, we can always start. Well, you know, we don't run the actual computation. We just analyze the job from somewhere else. So to get the input files, we need to go to a different folder, not to Theodore, because you don't have write access to Theodore. So that's, you know, we can call this tutorial, for example. then we go into tutorial, and then in this folder, we copy down this command from the tutorial. So we just get the input files. We get the input files for one of those jobs. So actually, what I can do is I can copy them to your folders if. Or I get to copy down this command. Then you get all the input files. So maybe here I can write it a bit bigger. So the command to get all the input files is what's shown here. Okay. I get to copy this down. Then you get the input files for the first job. Or if you can open the PDF file and look at the PDF file. Okay, you just want to send them the PDF file. Send them the PDF file. Okay. So Juan send you the PDF file. Then you can just copy paste this command out of the PDF file.
Yeah. I sent last night.
So you can just open. Juan, did Juan send you the PDF file tutorial3.pdf? Then you can just get it from the email. Then you don't need to download it via mobile extern. Okay. Okay, so now we're copying the data down.
Okay, now
Okay, so I think I'll just keep going with this, and then we can come back. So now, now if you copied the files, then now you can go into this new folder that we have, and if you look in this folder, then we have, we have the mold and input files, we have the orbitals, and then we have the output of the RSCC2 program, the turbomole rights, and then some more information about the coordinates. So then when we start Theodore, we always run Theodore int. This gives you the list of all different options. So Theodore already recognized this is 9. This is, this was written with the RSCC2 program. So Theodore usually already recognizes the program we use. So we use 9 for turbomole RSCC2. Then we have to tell it what is the output file. The main output file was rscc2.out. And then, here's some more options where you can take the default. So we say no here. Then also here we can use the default. We say yes here. We can say no to the charge transfer number analysis. So we say no to the charge transfer numbers because we don't want them in the first instance. So this is also the things that this says in the PDF tutorial. Yeah, so here's this question. Basically, you start here and you can kind of always press enter. Only here where it says this charge strength phenomenon, so we don't do that in the first instance, just to make things a bit simpler. Yeah, we do yes. So in theory, we do yes. So we say no to the charge transfer number analysis, and then we say yes to the natural transition orbitals, and then we just kind of press enter. So basically, we can always press enter except for when it says CT number analysis. So just to keep it a bit simpler, we say we always press enter except for the CT number analysis. Then we input is a bit easier. So then we have this file dense ana.in. If you want to look at it, you can see kind of, it's just a few keywords in there. You can adjust those manually, and then you run Theodore analyze Tden, and this calls the main Theodore program. But it's this PDF that's this PDF file is also an email that comes to send that. I think yes. So then we call Theodore, analyze Tden, and then usually when you run Theodore, the result always looks like this. So basically, this is just a list of the excitation energies, oscillator strength, and then these are the different Theodore descriptors. So PRNTO is how many NTO pairs you need. So you see all these states need two NTO transitions to describe them. So those are two different ways to compute the number of configurations involved. All these states in the form of aldehyde dimer are described with two electronic configurations, and that's also because you have two independent molecules. You also have these two configurations because we have the excitation on this side and the excitation on that side, so we always have two configurations, and that's the first thing you see here. And then we also see the root mean square electron hole separation. And you see this is very small for this one, kind of medium sized for this one, and larger for this one. So this is kind of the first Theodore run where you get some overview over the results when you run your test. Okay. Now then the point is that as a next step you want to look at orbitals, and the point is that Theodore generates lots of different orbitals because there's specific orbitals for every state, and that's why there are different scripts implemented in JMOL that make this very simple. So now it tells you, we have this JMOL file created, and we should run this command. So here it tells you, please run this command. Then we copy this in. So we run this command, jmol -n-nto jmol.sct. So we run this command from here. And then we get, then we run jmol automatically. And it should be running in the background now, and it produces files for all these orbitals. Yeah. Oh yeah, that's because option is found. Yeah, let's say on this keywords, it's just it prints out different analyses, but everything that things that is all it's not like so after you've run JMOL, then we should be able to see the orbitals. So we type ls, and you see you have all these different PNG files. So the point is, in principle, we should be able to open this HTML file, but I don't know if we have a. So let's say on the one hand, so we could open one of these PNG files in, for example, with events again. Doesn't let us know. So, What was that called? So,
but it doesn't work here because it's not installed
here. Yeah. So basically, I mean, if you're able to copy back the files, so let's say, maybe I can also kind of show you what it would look like if you were able to copy it back. So let's say we have our tutorial here, and if I'm able to copy this back, then I can have this HTML file, and this HTML file contains all the orbitals. So this is kind of how Theodore works if it does work. So then basically it prints all of this out, and then you have the orbitals here, and for formaldehyde, kind of this is an n orbital, and this is a pi star orbital. So in this case, the perspective is not ideal, but then you see the natural transition orbitals for the first state, natural transition orbitals for the second state, for the third state. So in this case, the pictures as such are not so exciting, but the point is that, if you have a complicated molecule, then you just run Theodore, and then you get this HTML file that contains all all the orbitals. So I mean, you know, this is an n orbital, this is a pi star orbital, this is an n orbital, this is a pi star orbital. You don't see it that well here. You know, if you want to make it a bit nicer, you can also run this interactively. So you open Jmol, and then you know you open this scripting file here, and what you can do is you know you can copy the commands from this file directly into Jmol. So then you open Jmol, you open the console, and then you can copy the file directly into Jmol. So then you can see the orbitals like this. But so then you can, you know, you look at this file in the console and copy the commands directly in. So then, you know, then we can take these commands from here and copy them directly into Jmol. So then it doesn't run it completely automatically, but then you see kind of how it renders the orbitals, and then you can see them a bit better if you change the perspective. So you can, so there's some ways how you can play around with that a little bit. Okay, and then you have the pictures rendered from a different perspective. Do you want to? I can send you the paper. So it's you know it's just one way of defining like the whole thing. So I can show you the paper later. But okay, so that's the one way. So I hope you kind of realize. So that's how we compute natural transition orbitals, and the idea is that you know that Theodore has these functionalities where we can you know get lots of orbitals, you know, where we can plot lots of orbitals automatically. So that's the point here. So even if it's a little bit clunky on your laptop, I hope you can kind of get this idea that, you know, we run Theodore, and then we get the natural transition orbitals for all the different states. And then we see, okay, the first two states are n pi star states. Then we have more n pi star states. And so on. And we get some convenient pictures for the states. So then I think now we can go to the second thing. So the thing that we still don't know is, you know, we know that there are n pi star states or you know, we can know what the orbitals look like, but we don't know if they're locally excited or charge transfer states. So then the next question is to find out if the locally excited charge transfer, and then we use this fragment-based analysis for Theodore. So basically, so then we run Theodore in, and for the second time Theodore in, we can really always take the default values. Okay, so we do this, and then we always take the default values until we're at this point fragment definition for charge transfer number. So that the thing is with this, you know, we divide. If you remember the talk today, we divide our molecule into our system into different fragments, and then we look at the local excitations and charge transfer between those fragments. So and the critical point is always that we have to define which atoms belong to which fragment. So in this case, you know, we have the molecules are going to be 1, 3, 5, 7 for one formaldehyde molecule, and 2, 4, 6, 8 for the other formaldehyde molecule. So So then we have to say, okay, atoms 1, 3, 5, 7 are going to be in one fragment, and atoms 2, 4, 6, 8 are going to be in the other fragment. So then in this case, we just say manual input. For small molecules, we can input things manually. For larger molecules, there's also this possibility for automatic generation of the fragments, but then you also need Avogadro. So then kind of the logic is a bit more complicated. So now we do the manual input, and for the first one we say 1, 3, 5, 7, and for the second one we say 2, 4, 6, 8. So you know. Because that's just how the atoms are arranged in the file. That 1, 3, 5, 7 are here, and 2, 4, 6, 8 are there. And you have the spaces.
Yeah, because I was typing directly without selecting.
So we have to do
Those things.
Okay, so the one critical thing for this charge transfer analysis is always we define the fragments, and then all the other things are more technical. So after you've defined the fragments, we can, we just press enter a lot of times and go through the other things. We don't need to worry about those, okay? So if you've done the fragment definitions, press enter a lot of times, and then we run analyze T then again. And then, then you should see this kind of output. Let me make it a bit nicer. If you run it here, you should see this kind of analysis, and this, this is the main outcome of this fragment-based analysis, and the main thing we're interested here is this charge transfer value. So you see the first 4 excited states have almost no charge transfer value, so these are these locally excited states, and then the 5th and the 6th state are charge resonance states. And kind of the important point is, you just kind of press a button, and then you can differentiate between this local and charge resonance states. And if you remember, it's kind of the same technique that we also had for this push-pull system, for example, or for the excitons in these conjugated polymer. So all of this goes via this kind of machinery. I'm just using this small molecule to illustrate this. So this charge transfer is the important thing. And then we already talked about kind of this number of configurations that is involved here. And then maybe something here, here comes the root mean squared electron hole separation. And then the states with large charge transfer have also larger electron hole separation. So that's a different way of looking at charge transfer. All right, so that's, you know, kind of the basic operation of Theodore. So that's the stuff that you know, kind of the basic thing that you do. You plot natural transition orbitals, or you plot, yeah, or you do, and then you do charge transfer numbers to get this decomposition into individual fragments. So let me just kind of move ahead a little bit. Okay, then the next thing that we're doing here, so do you remember when we had this conjugated polymer, we looked at this electron hole correlation plots, these matrix plots where the different tiles were either dark or light. So to get those, we used what's called Theodore plot frag. So the omega matrix is always kind of this matrix with the charge transfer numbers that tells us kind of where is the excitation localized, and then frag just means we compute with respect to fragments. So then the next script in the tutorial is this script. And okay, and then you call this. You press, in this case, you know, we can just press enter a lot of times, unless you have some kind of specific ideas about what you want them to look like. So, but again, we can just press enter a lot of times, use the default. And now if you press ls, then you see we have these new files called p color, and these new files now contain these charge trend, these electron hole correlation plots. So you remember in our talk where we had this structure of kind of this exciton with the hydrogen atom in the box. For the formaldehyde dimer, they look a bit simpler. So let me try to get those up. Well, it's delete eliminal, right? I guess, yeah. Okay. So then, if you can, then you can copy those back again. If you can't, then you just kind of have to trust me that this is how it works. So we look at those, and then you'd find a new HTML file. So the point is, you know, Theodore creates all these plots, and then several of these plots are collected into an HTML file just to make it easier to look at this. And then we have this HTML file, and we see now the first 4 states. Those were the locally excited states. There we are along the main diagonal going from lower left to upper right, and this means locally excited states. So this means local excitations on the first formaldehyde, this means local excitation on the second formaldehyde. And that's kind of the same for the first 4 states. And then these ones are different. This is a charge transfer from left to right. This is a charge transfer from right to left. So then this is kind of how you read these electron hole correlation plots for locally excited states to charge resonance states. And again, in our talk for this conjugated polymer, we showed a more realistic application of this, where we had this exciton in a box. But for here, you know, I just wanted to show you how to get all the scripts up and running for this first example. Okay, and I think just as a quick proof of principle, so for example, this was with turbomole, maybe many people are using Gaussian, so I just also wanted to show you that it works also with Gaussian. I'll just show you that quickly. So we we can copy this into our terminal. So then we copy now the information for the next thing. So basically the idea is, that these are the examples in the theater folders and just these standard tests. And then you can use these to play around. So if we go in here, you don't have to do this. I'm just trying to make this line a bit smaller so that it's not so as confusing that you can see this better. Don't do this. But so now the first command is that we can do a Theodore cc check Gaussian.log. So there's this external library called cclib that passes many different codes, and in that case it's good for us. You would just kind of check, is it going to be able to pass this at all? So then we just run the cc check command, and then it tells us, okay, we can pass this file, but we wouldn't be able to convert it to Molan form. It just as one utility here, and then we do a Theo in, but it's very similar to before. So only in this case we have to say 12 because we're using the cclib interface as external interface. Press enter, and then our file is Gaussian.log. We don't have a Molten file. And then we kind of do the same as before. We want transition densities. We want charge transfer numbers. We do the manual input in this case because we don't have kind of the other tools available. So we run that, and then the same init as before: 1357 2468, and then we just press enter a lot of times. And then we can run Theodore, analyze, Tden, and then we kind of have the same thing that we had before. Okay, so this is just kind of the take-home message is here. Theodore works with many different programs, so with different interfaces. So just kind of take a look if your favorite code is included or not. And then we see again we have the energies and the oscillator strength. The first one was with an ab initio method, CC2. This is TDFT, And you see, for example, that with TDDFT, you have low-lying charge transfer states that you didn't have with the wave-function-based method. So that kind of maybe the message here is that also Theodore kind of shows you problems of TDDFT that you might not see otherwise. So of course, when we run it with a different method, we get different results. So you can play around with this a little bit, and then we can go to the next one. It's hard to look at the Yeah, I remember. Yes, that's
But we can
So I guess you know or you can just cut the time, you know, you just see where does the last geometry start, and then you delete everything before that last geometry, and then just run it. And so it costs a lot of Okay, then I'll talk through the next things. So one point is, you know, in principle, especially when you have this fragment definition for large molecules, you don't want to enter all the numbers, and there is the possibility where you draw your molecule in Avogadro or pi mole, and then it kind of you delete the bonds between the atoms that shouldn't be bonded, and then you can insert that into Theodore. But for that, you know, you need Python Open Babel installed, and you need the Avogadro software. So we don't have that here, but just in principle, you know, there's some ways where you can make this input very quickly to get this fragment definition down, even for large molecules. It's not going to work here. So where, you know, in a tutorial where you see kind of this Avogadro window, we're going to skip that. We're going to do this manually. But please remember, you know, if you do this a lot, the tools exist and it's not hard to get them started. It's just we don't have them in this specific instance. So the next thing is, you know, we copy the input from the next bit. We go in here, then, you know, so if you install Open Babel, then you also have this kind of conversion tool. I don't know if that's going to work. Maybe I think it's going to work. Theodore Babel geom.xyz. So then, you know, this is just this little conversion tool where we can, you know, convert file formats. So that, you know, there's a small version integrated in Theodore, and there's a bigger version if you install Python Open Babel. So okay, but now that we have that, we can get started. So we do Theodore, Theo in, and then, you know, we can press enter, 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 and then here we have to use manual input now. So, you know, so it's always, if you don't know what to put in, just press enter. So usually the defaults work. Just if you have specific wishes, then you use something different. So then here we always have to use this manual input because we don't have the tools installed. But otherwise, you know, there's some tools where everything goes very quickly. So now we have our So here we're looking at the hexatriene molecule. So we have this molecule, and now we want to cut it into fragments where every one of these double bonds is its individual fragment. So this is how we're going to analyze this molecule. So then we have to enter this manually. It turns out the first one is 1, 3, 7, 9, 11. So just, you know, the atoms for the first molecule happens to be 1, 3, 7, 9, 11. Okay? So we enter this. Then we do the same for the second molecule, 5, 6, 13, 14. And then for the last one, 2, 4, 8, 10, 12. Okay, and then again, the fragment definition, that's always the one thing that we have to take care of ourselves, the one thing we have to think. Once we're done with that, we can just press enter a lot of times, and then everything just kind of works. Okay. So then we can run Theodore, analyze T then, and same as before. Now we get this information. So the one thing that people are always interested in for these kind of polyenes is that you have singly and doubly excited state. So the question is, you know, is the singly or the doubly excited state higher in energy? And it turns out for Theodore we use this value called omega. You remember I talked about this when we introduced one electron transition density matrices. And then we see, for example, omega for the first state is low, so this is a doubly excited state, and this is a singly excited state, and this is another doubly excited state. So in this case, for example, and we see directly the doubly excited state is lower in energy than the singly excited state based on these omega values. And as I said, kind of an ideal doubly excited state would have an omega value of 0. So here the omega value is 1.37. So this state still has about 38% singly excited character. So in the sense, you know, this 1/3 singly excited and 2/3 doubly excited. So the point here is that, you know, this omega value gives us some indication about which is the doubly and single excited, but also, you know, quantifies the admixture between single and double excitation characters. You know, and then let's say if the state is doubly excited, then all these measures don't mean that much. But for example, a single excited state, then we can also, you know, look at some of these other things. For example, we only have one configuration of, because it's kind of a pure homogeneous transition. Yeah. And I think that is one stage. So actually what this means is it's in the first symmetry transition between the first and the second symmetry and the second symmetry. So this is, and then the layer was not perfect. But the question was, so these are individual states.
Here doesn't like place one. This is the one.
You have to control it.
No.
Okay, then the next example I want to show you is you know, the idea of a transition metal complex. You know, we have our transition metal here, and then we have our ligands. So I'm just trying to draw this. So say we want to have, you know, our bidentate ligands. And here the point is, you know, if we look at our excited states, then we could have, you know, metal to ligand charge transfer. So if we start from the metal and go to the ligand, then we call it metal to ligand charge transfer. But we could also have, you know, a ligand-centered excitation. If the excitation starts in the ligand and goes to the ligand, or we could have metal-centered if we start in the metal. And now, kind of what we're trying to achieve here is that we run this computation on the transition metal complex and then get this decomposition into ligand-centered metal to ligand charge transfer, metal-centered, and so on. And if you remember, I kind of talked to you about this in the talk. So in the talk, this was fine-tuned a little bit, but in principle, we want to create this kind of a plot. If you remember, that's what I also showed you in the talk. Is it's kind of a representation. We have the excitation energies here. Then we could also color code the oscillator strength. I think in this case they're triple states, so we don't have oscillator strength. And then here we have the characters. So most of those are mostly metal to ligand charge transfer. So most of those are that we go from the metal to the ligand. But then, you know, the first three also have some ligand-centered character, and then the higher three states have some more pronounced ligand to ligand charge transfer. So ligand to ligand charge transfer means, you know, for example, we start at this ligand and go to this ligand. So now kind of what I want to show you is how to create these kind of plots, and I really think that, you know, that doing plots of this kind is more instructive than just having, you know, this large table with all the different canonical orbitals involved. So that's why I think it's important to look at how to do this. So we do the same as always and copy our input data here. And then we run Theodore in. So in this case, it doesn't detect which kind of QChem you're running. So we have to tell it we're running QChem. So we're running QChem as TDDFT job. The input file is qchem.out. We use state analysis. So basically in QChem, the main part of the work is done in QChem as such. And we're just with this libwfa module that I mentioned, and then Theodore just kind of post-processes this information. So we already ran state analysis. We didn't do time-dependent Tam-Dankov, so then we can just kind of press enter, enter, enter. In this case, again, we always have to do manual input because we don't have those tools installed. So we do manual input. And now we have to look what it says. You know, we have to use the data from here. So the first one is just 1. And for the second one, we can copy this. So we can copy this with commas. So we can just kind of so we can, you know, we copy this from the PDF into Theodore. You can just copy it directly like this and press enter. Then the same for the next one. Copy, paste, and the same for the next one. Copy, paste. Okay, and then we have this, and then here now we want to say special analysis of transition method complex. So first we paste these numbers in, or you just copy them down from the PDF, and then we can do this special analysis for transition method complex. Okay, so we need to use this number. So basically just enter all the atoms for the different ligands. And you know, if you have Python open Barbara installed, then you just kind of, then it all goes automatically. But in this case, you just have to enter those instances. Right now, they know it's the level is. So it's, maybe you can log in, log out. It's exactly what the X, so it's not the X. Okay, so then we can run this for transition metal complex, and then all the other ones we can again just kind of say enter, and then we run Theodore analyze Tden.
Okay, you know what it is?
Okay, so okay, so if we run this analysis, then we see that most of the states have about 50% metal to ligand charge transfer character. So the nice thing is, how this works, and you run the computational transition metal complex, and it tells you directly what is the state character. So then we see, then we just kind of press a button, and then it'll tell you, okay, this has 50% metal to ligand charge transfer character. And for example, you can also do this for dynamics. You run a long dynamics run, and the dynamics tells you how much metal to ligand charge transfer, how much ligand ascendant character you have, how does it change over time. So that's why it's sort of nice. And you see, okay, the first states have 30% ligand ascendant character, and then these later states have more ligand to ligand charge transfer. The nice thing is, you don't want to look at all these orbitals, you just want to press a button, and it tells you the state character. So then the next thing we wanted to do was to create this plot that we can actually use, in a paper to represent the character. So now, the way we have to think about it is, for example, we have all these different fragments. So iridium is going to be fragment 1, and then this ligand is fragment 2, this ligand is fragment 3, this ligand is fragment 4. And now metal to ligand charge transfer character in this case means that we go from 1 to 2, or we go from 1 to 3, or we go from 1 to 4. So metal to ligand charge transfer character means 1 to 2, 1 to 3, 1 to 4, for example. So then in the next thing we have to enter this. So the code that we use now is called Theodore plot bars. This creates these bar graphs, that I showed you in the talk for the push-pull system. So you can use the default here on fractal text, the file is produced. You can use the default here, and now our first component is metal to ligand charge transfer. So the first component should be the metal to ligand charge transfer character. And now, okay, you can use any color you like. And now we have to use this electron hole indices. So in our case, metal to ligand charge transfer means we go from 1 to 2, from 1 to 3, and 1 to 4. So we combine those three. In a simpler system, if you just have kind of a donor acceptor system, then then charge transfer character just means you go from 1 to 2. So in a simpler system, it's a bit easier. Or locally excited on the donor would be from 1 to 1. So in some cases, this assignment is simpler. Here, because we have 4 different parts, we have to think a bit more. So metal to ligand charge transfer is we start here and go to any of those 3 ligands. So then we have to say, okay, our first choice is 1 to 2. We go from the center to this one. Then the next pair is 1 to 3. We go from the center to this one. And the next pair is 1 to 4. We go from the center to this one, and now we press enter because we're done with this choice. Then we have to use our next choice. Let's say our next choice in this case might be called ligand to metal charge transfer. So that's kind of the opposite. So ligand to metal charge transfer and whatever color you like. Now now means that we go back. So now we have to go from 2 to 1, from 3 to 1, and from 4 to 1 for ligand to metal charge transfer. You have to go from 2 to 1, from 3 to 1, and from 4 to 1. And then press enter again. So again, we go from here to here, we go from here to here, we go from here to here. So press enter for that. And then the next component, you know, ligand centered. So then local, you know, the ligand centered is from 2 to 2. So we stay here. From 3 to 3, we just have a local excitation here. Or from 4 to 4, we have a local excitation here. So this would be ligand centered. So then whatever color you like. And then we say 2 to 2, 3 to 3, 4 to 4. And insert this. And then, okay, then you can do the same also for ligand to ligand charge transfer. So then, you know, those are all the pairs between those. So it's 2 to 3, 2 to 4, 3 to 2, 3 to 4, 4 to 2, 4 to 3. So then with all the mixtures between the ligands, I mean, you can kind of look what it says in the tutorial. So then we use this color. So we have 2 to 3, 2 to 4, 3 to 4, and then we have 3 to 2, 4 to 2, and 4 to 3. So I mean, you can enter this, or you can, you know, for practice purposes, you can also leave it empty if you want to. And then, okay, and then I mean, and then I think we'll leave it as it is. We press enter, and now it tells you, you know, you have to do this command, and this is probably not going to work. Yeah, so in this case, yeah, so in this case it doesn't work, but you know, in principle you can open this then with LaTeX, and so, you know, for example, just to give you an idea what this looks like in practice when you run this. So for example, you know, what the script does, it you know, it creates figures like these, like I showed you in the talk, where you have. So, you know, so basically, you know, what you were doing here is, you know, for a transition metal complex, you can create a figure like this, where you have the different energies. So these are the energies for a single state, energies for a triple state, oscillator strength. And then down here, you have the characters, you know, where you have the different ligand centered and metal to ligand charge transfer contributions. So basically, to create plots like this, we have energies, oscillator strength, and state characters together. So that's kind of what we did with this script. If it would have worked, obviously it doesn't come out like this straight out of Theodore, but you know, you can kind of use it as a starting point. How much time? So, yeah? 20 more minutes. How is that today? Okay. Yeah, it doesn't actually work. So you can press it. Yeah, that's this. I mean, usually we it's missing one library. Yeah, so Okay, so I just logged out. Okay, so I mean that one is now the script generates a LaTeX file, and then if you have the proper LaTeX libraries installed, so you need PGF plots installed, then then you can generate this figure that I showed you with LaTeX. So on this machine it's not installed, but that's kind of the workflow. Once you have that, then you can compile this with LaTeX. Usually, when you want to use it for publication or for a talk, then you might fine tune this a little bit, so then you can look at the source code at the LaTeX file and then just fine tune things. But it should kind of get the core together. So okay, so that's then the next thing is it's kind of this idea with conditional densities. If you remember that what I showed in this conjugated polymer, where you kind of move the hole through the system and the electron adjusts through the hole. So I don't want to do this now, but if you're interested, if you're working on these larger systems, then you can try this out. So I think this should be shown here. What I want to show you is this other script, and that's so far we've only done transition densities, but now the idea is kind of how to do state densities, and the idea is basically when you have a Molden file, you can run this script. So for example, often for these multi-reference programs, you have Molden files that contain the natural orbitals, but every DFT job gives you a Molden file. So then you can also compare between different DFT jobs, for example, DFT of the neutral system, DFT of the cation. You can use unrestricted DFT for the triple and so on. So this is a bit of a different way of operating Theodore. So I think we can do this, and then we're done for the day. So the next example is here. So okay, again, as always, we copy this in. Yes, please do what I ask you to do. And then it gives me an error messages in Spanish that doesn't exist because I didn't make, because you know I logged out. But now, okay, now it works. So you see here we have these Molden files, and of course these Molden files, you can open them with Molden. Oh. Yes. And for instance, you know, of course, it's a Molden file, so you can open with Molden and then look at the orbitals. But in our case, now we use, you know, we use this command Theodore analyze NOs, and that's, you know, that's a convenient command that whenever you have two Molden files, it allows you to run this analysis. The only thing that's a bit problematic about it is that the Molden files, they're different convention. You know, sometimes whether, you know, you have spin restricted or spin unrestricted orbitals. So there's some options here that you can use, and you know, in a sense, if you use the wrong options, then the results are completely meaningless. So in a sense, you know, it's you can kind of try out the options until the results make sense, or you kind of think about it in more detail. But so in our case, we have to use this -u option because we have unrestricted orbitals, because we have separate orbitals for alpha and beta. So then what we have to do is we have to say Theodore analyze NOs minus unrestricted, and then we say Molden.1, Molden.2, Molden.3. And then one thing to realize is that the first one is the reference state, the first one is going to be ground state, and the second and third one are the excited states. So then we run this, and this gives us a bunch of information. So maybe the thing that's easiest to start with is here we have the bond order. So for example, it tells us that atoms 1 and 3, they have a double bond with a bond order of 1.6. So then we said, you know, those two form aldehyde molecules. So 1 and 3 were those two. So yeah, between 1 and 3 we have a double bond in the ground state. Same between 2 and 4. And then, you know, within the excited state, the bond order is reduced because we excite into an anti-bonding orbital. So that's one thing, that we have the bond orders. Excited states bond orders are reduced. Then the other thing that's kind of convenient of this analysis is, for example, when we start. So this is now the ground state. Then we see the molecule populations for each atom. So these are the gross populations. So of course, so we have 5.9 electrons, but then the nuclear charge of the carbon atom is 6. So then of course the net population of these carbon atoms is 0.1, and for the oxygen atoms, you know, you have to subtract the nuclear charge of 8. So Theodore does not know what the nuclear charge is. So we just have the number of electrons, and in total we have 32 electrons. And then these are measures for unpaired electrons. So we're looking at these especially for systems with emerging biradical character. Then you see how many unpaired electrons are there per molecule. Of course, then in the ground state of like a closed shell molecule, these numbers are very small because we don't have accretion of unpaired character. Then, you know, here we're moving up to the excited state. So for the excited state, we also have this detachment and attachment population. So for example, we see that the excitation happens on the oxygen atom. So we have 0.45 electrons are detached from the oxygen atoms, and they're also attached to the oxygen atom. So So most of the detachment is on the oxygen atom, most of the attachment is on the oxygen atom, and a little bit attachment is also on the carbon atoms. So essentially, you know, we have this n pi star state where the n orbital is on the oxygen atom. That's why it's in the detachment, and then the pi star orbital is distributed over carbon and oxygen, but we also have more contributions from the oxygen. So this shows you, you know, where is the excitation localized now in terms of atoms. So this relates to what we talked about to this fragment-based analysis. Only here we see it in terms of individual atoms. But just to realize kind of the difference density is not exactly the same as the transition density. And then we also see now the carbon and oxygen atoms have lots of unpaired electrons. Because of in the excited state, of course, we create a biradical, and then we have unpaired electrons in the excited state. And down here you see the sum over all of them. So in total we detached 1.1 electrons and we attached 1.1 electrons. Yeah, and then you see this final summary. So there's again we have number of unpaired electrons, and there's this Y0 and Y1 are also measured by a radical character. Then eta, that's something from Peter Gale, that's got the excitation number, so those are both single excitations. And the promotion number, that's from the difference densities, that's how many electrons are rearranged. So then you also get this information at the end. Then yeah, and then for example, I mean, then you can open these in J-mole again. For example, let's say we can look at the NDO J-mole dot SPT, and you can either run it all in the background, or you can open J-mole. And you know, then if you want to see an orbital, you can copy from here into the J-mole console. Okay, so in this case, it doesn't like it. So if you want to run J-mole, you have to change the header here from capital letters Molden format to lowercase letters. And then then you can get some more orbitals. You can either use the J-mole script. So if you set the appropriate options, then you can also get Molden files directly and open those files with Molden, for example, if you prefer that. Okay, so that's pretty much all I wanted to show you. So I hope you get a bit of a feeling of how theater works. I mean, let's say the difficult is that you have all these different external tools. That theater is more like an interface between the quantum chemistry program and the visualization program. So that's why it takes a bit of time to set up kind of an environment where everything works. So let's say usually if I use theater, then I'd like to use some kind of remote connection. So you might have a Samba connect to your server, or you use HFS to connect to the server. So usually it's nice, if you can run theater on your local machine, then you can look at all the results that are produced on your local machine. So So it's a bit, it takes a bit of time to set up the workflow in the way that you have all the data ready, but then you also have an easy way of looking at the results that are produced. But otherwise, I hope you got a bit of a feeling. It's, when you actually do it on your own system, then it's much easier than kind of trying it on a remote cluster. So if you found it difficult, usually it's not as difficult, just spend an hour or two thinking about how to set up your environment, and then I'm sure it's gonna run nicely. And I'm always, if you end up using it, if you have some questions, I'm always happy to answer questions. I mean, you can answer via the official forum, then it's kind of documented, and then if anyone else has the same question, they can find it. Always happy to hear people are using it. And what I'm saying is that there's lots of different tools, and sometimes it's also just sometimes you don't even need Theodore as such. Sometimes you just have a Molden file with lots of orbitals, and you don't want to sit there and click on every orbital in Molden, but you want to just kind of generate all these pictures at once, and then you have something like Theodore JMOL MOs, and that's a little wrapper script that allows you to plot lots of orbitals in JMOL, Or sometimes you might have lots and lots of cube files of different densities, and and then you run some like Theodore VMD plots, and then you have a wrapper script that allows you to to plot lots and lots of cube files in VMD and so on. So I collected a number of tools there. If you're interested in automating things, then you can take some time, play around with it. If you have any questions or suggestions, let me know, and I hope you'll give it a try for your own molecules if you're working with solid states. Yeah, that's it.
Thank you.
Okay, so thank you very much, Felix. It was very nice to have you here 4 hours of theory and exercise. I apologize for the problems with the supercomputer center, but hopefully the next lecture they will not work still. It will not work still, but tomorrow hopefully it will work. So let me say 2 things. So after the coffee break, I'm going to create a document in Google, and I will send the link to you, because I need from all of you, even if today the computer works and everything, I will ask you to write there your name, surname, email, NIF or passport or whatever, so some identification number, and that's it, because we need it to fix everything in the computer. So the supercomputer center asked me for this information because they need all this information in order to create properly the accounts. I don't know why they didn't do it in advance, but anyway. But later I will create the document, and I will send by email the link, and then you fill the table, okay, with your information. And the second thing is, remember that all these lectures, both the theory and the computer exercise, are recorded, and they are available later in the YouTube channel, so you can visualize them later, and you can do it again if you want the Theodore tutorial, but also the other tutorials. Okay. Okay, so now we have a coffee break, and we are back at 6:20. Okay.
Okay. Thank you.
Sorry, don't leave anything here, because this room can be opened with the university card. Any professor can open the room, so just in case, don't leave anything here.